Hello, stats class. Here's the beginning of chapter 5, which is all about probability. And I will tell you the first part of these notes you'll probably have heard, probably get it, have heard before in other classes, but then we will very quickly get to stuff you have not heard yet, most likely. So probability, the informal definition, is chance or likelihood. How likely is it for something to happen? Sometimes it's put in terms of risk. What's the risk that something, if it's a bad thing, would happen? So in other words, how likely or unlikely something is to happen. And as you probably know, if something is certain to happen, that's 1, probability of 1 or 100%. If something is impossible, that's a probability of 0 or 0%. And most of the time we work with probabilities that are in between these two. Because it's hard to think of something that is absolutely impossible. For instance, you flip a coin and you might say that the chances of it landing on its edge are impossible, but then somebody might argue, oh no, there's a really small possibility that that might actually happen. So we're mostly going to be working with stuff that's not exactly 0 or 1, but somewhere in between. And a few types of probability: experimental versus theoretical. Experimental probability is probability that you find out the value by trying it, by trial and error. So you just do it a whole bunch of times and see how many times it does a certain thing. And so we call the thing you're interested in is called the event. So this symbol just means probability of an event, is officially defined as, I'm going to write this in words, the number of times it happens when you try it, divided by the total number of trials. And that's actually where the statistics comes in, because if you just try something a bunch of times, you're basically taking a random sample of all possible coin flips or all possible whatever it is you're trying, and those trials become your sample, and then you see how many times it actually happens in all of those samples. So it's basically based on what does actually happen. And if you don't know the theory, you can't do theoretical, which is what we're going to talk about next. Then all you can do is an experiment and try it and see what happens. So that's called experimental probability. The other kind is theoretical. So that's when you get into the pure or not applied mathematics. It's possible sometimes to calculate what ought to happen, and that would be called theoretical probability. So in that case, the probability of an event would be the number of ways it could happen divided by the number of possible outcomes. And when I say it, I'm talking about the event that we're interested in. And that event could be a coin landing on its head, it could be a die landing on an even number. There's a lot of different things it could be, and we will do a lot of them in this chapter. So experimental is based on what does happen when you try it. Theoretical is based on what could or should happen if you could theoretically do it infinitely many times. And we'll be learning how to calculate those theoretical probabilities. That's a big theme of this chapter. If you didn't like chapter 4 because it didn't have enough math in it, the math is coming back in this chapter. And I don't know, that's good news to me because I like math. For some of you, you kind of liked the vocab stuff better. So here's an example of both of these things. Probability of getting ahead when you flip a coin. I'm going to do theoretical first. Theoretically, there are two possible outcomes for a coin. It could be a head or a tail. And so that's one way to get a head out of two ways to get answers in general. So there's one that's a head, and there's a head or tail possibilities on a coin. And so that's 50% or 0.5 chance of getting a head. And that's, of course, if you assume that the chances of it landing on its side are so close to zero that we can ignore them. Or I suppose there's a tiny little chance that your coin will roll down into a crack in the sidewalk and never be seen again, and then we wouldn't know which way it landed. We're going to ignore all those itty bitty probabilities and say there's a half a chance that it will be a head and half a chance it will be a tail. That's a theoretical probability. Experimental would be if you actually flipped a coin over and over. So for experimental, what you would do is you'd say my probability of heads is how many times it came out heads when I flip it, however many times I'm willing to flip it. So maybe I decide to do 50 flips in a row like we did in the warm-up. Actual number of flips. And on the top is how many heads I got, actual number of heads, which may or may not be exactly half, as you found out in the warm-up. So the exactly half sometimes happens, right? But I might not get 25. I might get only 17. And that's okay. That's a perfectly good experimental probability. This comes out to 34%. Or somebody else might get 27 out of 50, and then they'd have 54%. And so this one varies depending on how your experiment comes out. And that should sound familiar to you because we're used to samples not necessarily perfectly representing the population. The population is all possible coin flips, which have a 50-50 chance, but then our sample might be 17 out of 50 or 27 out of 50 or anything else. Theoretically, it could even be 50 out of 50. Crazy. So samples would come close to the population most of the time and not always. So one of the most important things, I would say probably everything I've done so far is stuff you've heard before. I'm kind of making an assumption there, but there are things that are covered in other classes. Then we get into the stuff that's specific to AP statistics. And one of the big things you'll be asked to do in your homework is interpret. What does that 50% actually mean? So when I say the probability of heads is 1/2, I don't mean that every single sample comes out as 1/2. I just said that a minute ago. But what I really mean is it's the long run value if you did it so many times that it would even out to be close to the theoretical. So the long run value is a really important concept. There was a famous statistician, I forget his name, but he was a prisoner of war during World War II, and he wasn't locked up in a terrible prison. I mean, he had a room and he had some stuff in the room, and one of the things he had was a coin. And so being a statistician, he said to himself, I'm going to flip the coin over and over again and keep track of my results. And he started getting nervous around 300 or 400 flips because he wasn't at 50%. And he's like, oh, I feel like it ought to be 50%. So he kept on flipping. And by the time he got out of prison, he had like 10,000 flips recorded from an actual coin because, you know, he had nothing better to do. And it did end up closer to 10,000 or closer to 50-50 when he got way up there. So the idea behind a long run value, sorry for the sidetrack, but it was an interesting one, I thought, is if I flipped many, many coins, like if I imagine going to infinity, I expect in the long run that about half of them will be heads. And that's just imagining what would happen if I could go on forever. And I'll show you a picture of that in just a minute. But before that, I want to go back and say, I'm not using the word chance or likelihood or any of those informal words in my interpretation. One of the things I'll ask you on the quiz, I'm going to give you fair warning in advance, is I'll ask you to interpret without using any of those words in your interpretation. And what you should be doing for that is you should be talking about, if I did this many times, this is what I expect to happen. So that idea is also called the law of large numbers. Isn't that a great name for it? There used to be an applet that I can't find anymore. They took the site down, so I won't show you it digitally. But let's just talk about what if I made a graph of my cumulative probability. So imagine I'm this guy who's in prison and I'm flipping coins over and over again. This is the flip number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it just keeps going and it keeps going and it keeps going. And here I'm going to graph the probability. Actually, I'm going to graph the cumulative, there's a good word, probability of getting ahead. And it could go anywhere from 0 to 1. So let's say on my very first flip, by the way, 0.5 is here, that might be important. On my very first flip, let's say I get a 1, or ahead, I mean. So then after that first flip, it kind of looks like I have a 100% chance of getting ahead, right? But it's not, you know it's not. So maybe my second flip might come out to be tails. If my second flip comes out to be tails, then all of a sudden I'm at 50%. If my third flip also comes out to be tails, now I have a third of my 3 flips are heads, and so I'm about here, about a third of the way up. And then maybe my next flip might be heads again, and then my next flip might be heads again, and it kind of goes up and down and so forth until it eventually should level off at 50%. So it goes up and down and then it levels off is basically what's happening here. So that is showing you that in small numbers, you get wide variations, and then the bigger your sample size is, the closer you get to the theoretical probability. And that's what the law of large numbers says, is that more trials, which would be a bigger sample, gets you closer and closer to the theoretical probability, which is why this statistician who did the coin flips, I only need one L there, probability, why he eventually leveled off at 50%. And I just spelled probability wrong, which is embarrassing. I'm fixing it. Probability, sorry about that messiness. So what's interesting about that is some people might think that it would level off sooner than it really does, but it does eventually level off. And you see that in other areas too. So let's think about grades for a minute. Grades tend to vary widely at the beginning of the quarter. Have you ever noticed that you do one thing and suddenly your grade goes way up or goes way down because of that one thing you did? Later on, towards the end of the semester, it's harder to change your grade. If you haven't noticed that, you should pay attention to that because it's kind of important. What that means is your grade is leveling out towards what is a fair grade for you. And so maybe you really do understand 80% of what's done in class, and that's what your grade should level off to if the grading system is fair. And so that's why teachers don't worry as much as students about grades at the end of the semester. They're like, it's going to level off to what is a fair grade for you. And at the end of the semester, if you're trying to bring your grade up, you're trying to show that you know more than what you knew before. It doesn't work very well. So I've kind of done a few sidetracks, which made these notes longer than they should have been. Sorry about that. But I have 2 more things to talk about. Actually, maybe 1, but it's got 2 pieces. Let's talk about myths about probability, which you as AP Stat students are going to try to avoid because you are smarter than that. There are 2 myths that are common out there that people actually believe. And the first one is called, I'm on a roll. Or sometimes it's called the hot hand theory. This happens mostly with people playing games that have a lot of chance in them. So if you have a game where rolling a 6, for instance, on your die is really good, and you happen to roll a bunch of 6s in a row and get some kind of a run or streak of 6s, one of the myths is that because this happened, because I just had many similar outcomes, that I'm going to have more of them. So the people who believe this tend to believe that you are more likely to get that same outcome again than what would normally happen with theoretical probability. So they think that because I just got a bunch of sixes that I'm on a roll, I'm gonna get more sixes. When really the 6 is still 1/6 likely to happen. I'm sorry to tell you that. The other myth is the opposite, which I could best phrase by saying I am due for, like, I haven't had a 6 in a long time, and therefore I'm due for a 6. I've got to have a 6 because I just haven't had one for a while. I must be more likely to get that. So once again, it's people who have many similar outcomes in their chance, whatever they're doing. And they think because of that, it's less likely to happen again. And what these people are thinking is they are thinking about this thing that they call the law of averages, which doesn't really exist as a law, but people believe it, or I call it the law of small numbers. And it's awfully tempting to believe this because this actually does really happen if you have large enough numbers, if you go into the thousands of trials. But if you have like 5 heads in a row on a coin, that does not make the next one more likely to be a tail. The next one is still 50-50 chance. So that's kind of interesting that both of these are not true. And the reality is that if you have independent events, which we're going to talk a lot about those this chapter, independent events like coins or dice or things like that that don't depend on each other, they have no influence on what happens next. That means that what happened before does not affect what is going to happen. And that's sometimes called the memoryless property of coins or dice or whatever, where the coin or the die has no brain, of course, and so it doesn't actually remember what happened before and try to make it the same or different. Um, and so therefore it can't change its probability of what's going to happen next. Now, the place where people really get hung up on these myths is if it's not just a coin or a die, but if it's something that takes skill. And people have actually, statisticians have actually analyzed things like free throws in basketball and home runs in baseball and things like that to see if streaks actually made that player more likely to keep going with the streak or if it made him less likely to keep going with the streak. And they couldn't prove either one of these. It turns out that once a person's probability of getting whatever it is, a free throw or a home run or whatever, once that's determined, that it pretty much stays the same probability in the long run. Maybe not in the short term, the small numbers, there might be a streak, but in the long run, it really doesn't change a lot for a particular person. And so that's something that's hard for people to believe when it has skill involved and not just luck. But if it's just luck, like a coin or a die, I'm sorry, these myths are definitely false. So kind of inconclusive evidence about the sports things, but about the gambling and chance type activities, these are myths. Don't fall for them, and you'll have to explain some of that in your homework. So that is it for today's notes, and we'll continue Monday.